Okay, so we're going to start E4.1, which is exponential functions. So I'm going to go ahead and give you the definition of exponential functions, and then we'll go over what they look like, talk about domain and range, and then we'll look at how to transform them. Okay. So to get started, I need to go ahead and give you a definition of exponential functions, which is let A be a fixed, positive real number not equal to 1. Not equal to 1. Then the exponential function with base A is f of x is equal to a to the x. Okay. So we're letting a be a fixed, meaning it's not going to change once we have our base, that it stays our base. Positive real number. The reason we say positive is, remember, negatives when we're graphing represent reflections. So we always start off with just a positive base. And it can't be equal to 1, because notice if I did 1 raised to a certain power, no matter what power I raise 1 to, it will always be 1, right? So that would just make it a constant function. So we don't want to use 1, we want to use things bigger than 1. So whatever our base is, our function will just look like this. F of x is equal to that number raised to the x power. So I want to show you a couple of examples here, looking at different bases. Okay, so notice if a is greater than 1, okay, meaning our base is a number bigger than 1, then our function is increasing. I'm just going to say increasing, meaning it starts off small and our y values increase, they get bigger. If our base is between 0 and 1, then our function is decreasing. Okay, so that helps a little bit when we're working it out to know the general shape. So I'm going to go ahead and just work through a few of these so that you get the idea of how to make an xy table. So we're going to use the example f of x equals 2 to the x. Okay. So here, if I want to just plug in some points to get a good picture, 2 to the x, so 2 to the negative 2. Remember in 118 we went over negative exponents, move them across the fraction line. So it flips this. So this basically means 1 over 2 squared, which we know to be 1/4. All right, so I'm going to go ahead and put 1/4 here. When I do 2 to the negative 1, same thing. 2 to the negative 1, the negative exponent flips it. So I get 1 over 2 to the first power, which is just 1/2. And then I have 2 to the 0. Good important thing to note, which I forgot to note in 118, I apologize. Anything raised to the 0 power is 1. And the reason why, I'll give you a quick little spoof of that. Remember if we had something like 2 to the 5th over 2 to the 3rd, this is the same as 2 to the 5 minus 3, right? If we bring this one to the top, which gives me 2 squared. Okay, I want to use the same idea, but what if this was a number over itself? What if this was like 2 to the 5th over 2 to the 5th? We know that any number over itself equals 1, correct? But using our subtraction property here, this would mean that 2 to the 5th minus 5, which we would get 0. So notice 2 to the 0 has to equal 1. Okay? So any number raised to the 0 power will give you 1, regardless of what that number is. That's just the y, that's true. Okay? So 2 to the 0 is 1, and then 2 to the first power is 2, and 2 squared is 4. Okay. So I'm going to go ahead and go down here and graph this. So at negative 2, I'm at 1/4. At negative 1, I'm at 1/2. At 0, I'm at 1. At 1, I'm up at 2. And at 2, I'm up at 4. So notice if I connect my dots, I'm getting a shape that looks something like this. Now a couple of things I want to point out is, if I were to keep plugging in negative numbers, if I were to plug in something like negative 6, okay, notice what I would get is 2 to the negative 6, which is 1 over 2 to the 6, which is something like I don't know, 1 over 64 maybe, something like that. So it's a teeny tiny number. So if I go all the way out here to negative 6, 1, 2, 3, 4, 5, 6, I'm getting something that's really, really close to 0, right? So this is just still going, but it's getting really close to 0. But notice, because every time I plug in a negative exponent, it flips it upside down, and it just gives me a smaller and smaller and smaller fraction. This is never going to touch the line 0, and it's never going to be negative, because all it does is flip that fraction and make the bottom bigger, which means I'm getting closer and closer and closer and closer to 0, but not touching. When we get something closer and closer to a value without touching it, that's called an asymptote. So I'm going to go ahead and just put a dotted line here on my x-axis, and this is an asymptote at the line y equals 0. What that tells me is that my y values are getting closer and closer to 0, but they're not touching. Okay? All exponential functions have an asymptote. The other thing I'm going to point out really quick, which you'll see when I do this next example, all exponential functions in their most basic form go through the point 0, 1. And the reason is any number raised to the 0 power equals 1. So regardless of what the base is, when you look at an exponential function in its most basic form, it will always have an asymptote, and it will always go through the point 0, 1. Okay? So let's test that theory and look at this second example. The second example is f of x equals 1/3 to the x. So here, if I plug in 1/3 to the negative 2, again, the negative exponent flips it. This gives me 3 over 1 squared. 3 over 1 is just 3, and 3 squared is 9. Okay. When I do 1/3 to the negative 1, the negative flips it, so I get 3 over 1 now to the positive 1, which is just 3. Okay. 1/3 to the 0, anything to the 0 power is 1. That gives me 1. 1/3 to the first power is 1/3, and 1/3 squared gives me 1/9. So let's plug this one in and see if we get the same type of shape. So at negative 2, I'm up at 9. Okay. At negative 1, I'm up at 3. At 0, I'm at 1. At 1, I'm at 1/3. And at 2, I'm at 1/9. So notice we do get kind of the same shape. The only difference is our points are a little bit further apart. It's because 3 is a bigger number. But notice, I still have an asymptote, right? Here, my y values are still approaching 0 on the right side. So y will never be able to equal 0, which means that I have an asymptote at y equals 0. And notice, just like the last graph, it goes through the point 0, 1. Okay? So what I want to point out to you is, we talked about this above, where if the base is larger than 1, it's increasing. So here on our first example, our base was 2, which is larger than 1. So notice as we go from left to right, our y values, or our line, shoots up and increases. Okay? On our second example, our base was between 0 and 1. It was a small fraction. So notice we start out really big, and then as we go to the right, it goes down really small. So it's a decreasing function. Okay, so knowing whether or not it's increasing or decreasing based on the base gives us a good idea of what the original picture looks like. Now, when we transform these, I usually make you graph the original picture when we're practicing, just so you get a good idea. But if you don't like to do the extra work, which a lot of people don't, if you can remember if it's increasing or decreasing, how it should look, then you'll be good. Okay. So I just want to put down here, increasing function with. So what this says is, as x gets bigger, so does y. So notice as we go out in the positive direction for the x's, notice our y's are increasing. Okay, that's all that means. And then with a decreasing function, as x gets bigger, y gets smaller. So notice as we go out in the positive direction for x, notice our y's are getting lower. Lower and lower and lower. Now they're not actually going to equal 0 and they're not going to get negative, but they're going to keep going lower and lower and lower because we're going to keep getting smaller and smaller and smaller and smaller fractions as infinitely close to 0 as we can get. Okay. All right. And then the other thing I want to point out on here, a good note for all exponential functions, both graphs have a horizontal asymptote at y equals 0, and both contain the point 0, 1. Okay, so all exponential functions in their most basic form contain the point 0, 1 and have a horizontal asymptote at y equals 0. So now that we can see how to figure out what their base form looks like, their most basic form of the graph, what that picture looks like, now we're going to start doing transformations like we did before. So to do transformations of exponential functions, we use I'll call it the HSRV method, okay, which means we look for horizontal shifts, then we look for stretching and compressing, then we look for reflections, and then we look for vertical shifts. So let's go ahead and look at an example. And this first example has a typo on it, so I'm going to mark it out and rewrite it. This is supposed to be f of x equals e to the negative x plus 1. Okay, so I apologize about that. Now, before I get into this, I do want to point out, remember when we looked for horizontal shifts, we looked inside the function, because whatever happens to x happens inside the function, and whatever happens to y happens outside. So if I happen to have something like, I don't know, g of x equals the square root, okay, things that happen inside here happen to x, things that happen outside the function happen to y. The same thing is true with exponentials, but now notice where x is. X is up here in the exponent. So now our quick reference, or our shortcut in our brain should be, whatever's happening in the exponent is happening to the x. Anything happening outside of the exponent happens to the y. Okay? So for this function in particular, I have two transformations. I have a plus 1. The plus 1 is happening in the exponent, so it's affecting the x variable. X's are backwards from what we would think, so this means that when we add 1, we're actually going to go to the left 1. So next to h, I'm going to put left 1, which means I need to subtract 1 from my x's when I do my xy tables. Okay. The other transformation I have is a negative. Negatives are reflections, so that's my r, and it's going to be a reflection about the y, because here the negative is on the x. If we negate all of our x's, that flips it across the y-axis. So this is about the y-axis, and we get that by negating the x's. Okay, we don't have any multiplication, so there's no stretching. We don't have any addition or subtraction outside the exponent, so there's no vertical shifts. So when we did transformations before, we knew how to pick our xy table, right? If it was a square root, we started with like 0, 1, 4. If it was a parabola, we took like negative 2, 0, 2, that kind of thing. The same thing is true here, but we start out with whatever our exponential base is here. So I'm going to go ahead and just put here, for this function, okay, our parent function would be e to the x. We take the positive form of the base, which in this case is e, raised to just the positive x. So if I want to make an xy table, and I always include 0, because remember we talked about the point 0, 1 is on every exponential graph. So I'm just going to pick negative 1, 0, and 1. If I do e to the negative 1 power, and e is a button on your calculator, e is approximately 2.71, so you can just use that value, or you can use the e to the x or the e button on your calculator. So if I do e to the negative 1, basically what I'm doing is 2.71 raised to the negative 1 power which is roughly 1 over 2.71, right? And if I divide that out, I'm just going to use an approximation. I get like 0.36, something like that. Okay, let me erase this. If I do e to the 0 power, okay, that just gives me 1. Any number raised to the 0 power is 1. And then e to the first power, don't write it as e, because that doesn't help us when we do our transformations. E to the first power is 2.71. So now I have my function. I have my original parent function. I'm going to go ahead and graph it just so we can see what the base looks like. Now notice I just told you that e is approximately 2.71. So if our base is bigger than 1, this should be increasing. Okay? So notice at -1 I'm at 0.36, at 0 I'm at 1, and at 1 I'm at 2.71, which is roughly somewhere in there. Okay, so this is what my original function looks like, and now I'm going to transform it. So when I transform it, first thing I do is my horizontal shift, so now it looks like e to the x plus 1. To move it left 1, I'm going to subtract 1 from my x's. So I take my x's from the previous table, subtract 1. -1 minus 1 is -2. 0 minus 1 is -1. 1 minus 1 is 0. My y's stay the same, 0.36, 1, and 2.71. And then the last transformation I need to do is my reflection about the y-axis. In order to reflect it about the y-axis, I negate my x's. So I take my x's from the previous table, and I change their sign. I have +2, +1, 0. My y's are +0.36, 1, and 2.7. So I'm going to go ahead and graph my finished product here. Okay, so this is my function I'm hoping to graph. So I'm going to go ahead and go to where x is 2, and I'm now at 0.36. When x is 1, I'm at 1. And when x is 0, I'm at 2.71. Okay. So notice my function looks something like this. Now something to consider is we always have to know where our asymptote is. Every exponential has an asymptote, so we need to be aware of that and state its location after we've graphed it. So notice with my purple function, it's looking like this, right? And then if I move that left 1, notice if it's approaching 0, okay, it's still going to be approaching 0. If I move it to the left, it's just going to be approaching 0 a little further over. And then I reflect it about the y-axis, which turns it like this, right? So notice it's still approaching 0, but it's approaching 0 from the opposite direction, which is fine. It still means our asymptote is at y equals 0. Let me go ahead and put that on here. Asymptote at y equals 0. And then I'm going to write my domain and range based on my final graph. So notice my blue picture, it's going to keep going in both directions, left and right, which means my domain is -infinity to +infinity. And when I look at my range, I go to my lowest y value, which my lowest y value here is my asymptote, right, at y equals 0. But since it can never touch or cross y equals 0, I'm going to use a parenthesis to not include that 0. So it's going to go from 0 on up. It keeps going north, so on up to +infinity. Okay. So we take the base that they give us, create a table based on the most basic form of that exponential, then we transform using XY tables, and then graph our new function, identify the location of the asymptote, and domain and range based on our new function, okay, or our new picture. Let's look at another one. Same idea here. First thing I do is identify the parent function. Okay. When I identify the parent, all I need to know is what is the base of my exponent. So here this means that my parent function is going to be 5 to the x power. So I'm going to go ahead and go down here and just make an XY table of 5 to the x power. Now, a lot of people always ask me, how do you know what points to pick to put on your XY table? Well, I think about it. If I pick -1, 0, and 1, I'm only going to be raising 5 to the first power. If I pick -2, 0, 2, I'm going to have to square 5, right? If I square 5, that gives me 25, which in this case, I only have a 12 by 12 graph. So I'm just going to pick -1, 0, 1, because I know those points should all end up on this graph. If I do 5 to the -1 power, remember that flips it, So I would get 1 over 5 to the first power, which is then just 1/5. Okay. 5 to the 0 power is 1, and 5 to the first power is 5. So I'm going to go ahead and graph so that I know what my original function looks like. Notice my base is larger than 1, so it should be increasing. At -1, I'm at 1/5. 0, I'm at 1. 1, I'm up at 5. Asymptote at y equals 0, and it's an increasing function. So now let's identify what transformations have happened, see what it looks like now. So I have a -2 in the exponent. If it's in the exponent, it's affecting the x variable. X's are backwards from what we think, so this is actually going to move us right 2, which means I need to add 2 to my x's. Okay. And then the +3 is not in the exponent, which means it's being applied to the y, which moves it up 3. So I'm going to add 3 to my y's. I have no multiplication, which means no stretching and compressing, and I have no negatives, so no reflecting. So I'm going to take my parent function, which I already have a table for down here, and I'm going to move it right 2. So now it looks like 5 to the x minus 2. To move it right 2, I'm going to take my previous chart, my parent chart, take its x's, and add 2 to them. So -1 plus 2 is 1, 0 plus 2 is 2, 1 plus 2 is 3. My y's stay the same, 1/5, 1, and 5. And then I'm going to move the whole thing up 3 by adding 3 to my y's. So my x's stay 1, 2, 3. When I add 3 to my y's, 1/5 plus 3 is 3 and 1/5. 1 plus 3 is 4. 5 plus 3 is 8. Okay, so this is my finished chart. I want to go ahead and graph these ordered pairs. So when x is 1, y is 3.5. Sorry, 3 and 1/5, not 3.5. At 2, I'm at 4. Okay. And at 3, I'm at 8. Okay. So notice now my function looks like this. So I still need to know where my asymptote is. So if I look at my original purple picture, it's looking something like this, right? It's approaching 0. When it's approaching 0 and I move it right 2, if I move it right 2, notice it's still approaching 0, and then I move it up 3. So now, instead of approaching 0, if I move it up 3, it should now be approaching 3. So my asymptote in this case is up here at y equals 3. Now on your worksheet that goes, I just spelled this wrong, asymptote at y equals 3. If you have a worksheet that goes with this section, on the worksheet you have to identify the domain, range, and location of the asymptote. Make sure you put y equals, don't just put 3. Okay, it has to be y equals 3 because it's a line that it's approaching but not touching. And then when you draw your graph, make sure your graph doesn't cross that line, okay, because it's an asymptote. All right, so I'm going to go ahead and identify my domain and range based on my new blue picture. Domain, it's going to keep going left and right, so -infinity to infinity, which is true of all exponentials. They always keep going left and right in both directions. Regardless of what you do to them, always, all real numbers on the domain. Okay, the range, my lowest y value here would be 3. I'm going to use a parenthesis because it's not included. And then it goes on up to positive infinity. Okay, let's look at a few more, and then I'll let y'all try some. Okay, on this one I have a different base. So again, I'm going to identify my parent. My parent function in this case is 1/2 to the x. Remember, I don't take the negative. I always take the positive form of the base. So I'm going to go down here and go ahead and make 1/2 to the x. I'm going to go ahead and make an ordered pair xy table. And here, notice 1/2. 2 is the number I'm going to be working with, right, or 1/2. If I do 1/2 to the first power, it's 1/2. If I do 1/2 squared, that's 1/4. If I do 1/2 to the third power, that's 1/8. All these numbers are going to show up on this xy table, and they'll be on my 12 by 12 graph. So here you could do negative 1, 0, 1, you could do negative 2, 0, 2, you could do negative 3, 0, 3. Because this is a small number, it'll fit. I'm just going to do negative 2, 0, 2 so we get a good picture. Okay? 1/2 to the negative 2. Okay, negative 2 flips it. I'll write it out. I'm going to erase this here in a minute. So 1/2 to the negative 2, that flips it, makes it 2 over 1 squared. 2 over 1 is just 2, and 2 squared is 4. Okay. 1/2 to the 0 is 1, and 1/2 squared is 1/4. So I have my parent table. I'm going to go ahead and graph it. When x is negative 2, I'm up at 4. 2, 3, 4. When x is 0, I'm at 1, and when x is 2, I'm at 1/4. So notice my base was between 0 and 1, so it's a decreasing function. My asymptote is at y equals 0. So let's go ahead and identify the transformations. I have a negative on the outside of 1/2. Since the negative is not in the exponent, it's being applied to the y. If I negate the y's, that flips it, a reflection about the x-axis. I'm going to go ahead and put here, I negate my y's. I have a plus 3 in the exponent, which is a horizontal shift. Plus 3 actually tells me to go left 3, which means I need to subtract 3 from my x's. And then my plus 2 outside of my function tells me that I'm going up 2. I'm going to add 2 to the y's. Okay, I have no multiplication, so there's no stretching and compressing. Let's go ahead and create the tables. To move it left 3, now my function looks like 1/2 to the x plus 3. So I need to take the x's from my previous table and add 3. Oh, I'm sorry, subtract 3. Subtract 3 from them. So negative 2 minus 3 is negative 5. 0 minus 3 is negative 3. And 2 minus 3 is negative 1. My y's stay the same. So 4, 1, 1/4. Then I want to flip it about my x-axis. So I put my negative in, negative 1/2 raised to the x plus 3. To flip it about the x-axis, I'm negating my y's. So I change the sign of my y values, which makes it negative 4, negative 1, negative 1/4. X's stay negative 5, negative 3, negative 1. And then my last shift is to move it up 2. I have negative 1/2 to the x plus 3 plus 2. Move it up 2. I take my y's from the previous table and add 2 to them. So negative 4 plus 2 is negative 2. Negative 1 plus 2 is 1. Negative 4 plus 2 is positive 1 and 3/4. And my x's stay the same. Okay, so I'm going to go ahead and graph my new function. This last table gave me my ordered pairs. So at negative 5, 1, 2, 3, 4, 5. I'm down at negative 2. At negative 3, I'm up at positive 1. And at negative 1, I'm up at 1 and 3/4. Okay, so I'm going to go ahead and guesstimate that it makes a shape like this. But I'm going to go ahead and think it through. This was a decreasing function. That means I started out with a shape that looks like this. Okay, it's approaching 0. If I move it to the left 3, notice, still approaching 0. And then I reflected it about the x-axis, so that flipped it down. So notice it's still going to be approaching 0, but now from the underneath. Okay, so it's still approaching 0, and then I went up 2. So now instead of approaching 0 from the bottom, it's going to be approaching 2 from the bottom. So I drew my picture correctly, and I have an asymptote up here at y equals 2. Y equals 2. And then I'm going to go ahead and find my domain and range based on my new picture. So domain always keeps going in both directions, so negative infinity to infinity. My range, my lowest y value in this case is negative infinity because it keeps going down and down. My highest y value is at 2. I do not include it because it's never going to touch or cross 2. Alright, let me see. I'm going to do one more, I think, and then I think I'm going to let y'all do the next 3. let me do this one. I identify my parent. My parent function is just the base, which is 1/3 here. My parent function is just 1/3 to the x. So I'm going to go ahead and go down here and make a 1/3 to the xy table. Now, when we look at 1/3, I'm looking at the number 3. If I square 3, that's 9. 9 is still on my graph. If I cube 3, that's 27, not on my graph. So I'm going to use -2, 0, and 2. Okay. If I do 1/3 to the -2, that flips it, which makes it 3/1. And then square it, that gives me 9. 1/3 to the 0 is 1. 1/3 squared is 1/9. I'm going to go ahead and graph it. It should be decreasing because 1/3 is between 0 and 1. So at -2, I'm up at 9. 1, 2, 3, 9. At 1, I'm up at 1. And at 2, I'm at 1/9. So notice it's a decreasing function with my asymptote at, it's really not straight, with my asymptote at y equals 0. Okay. All right. So now I want to go ahead and just figure out what transformations have happened. Now it really bothers me when they don't write the x first in the exponent. So if it helps you, you can rewrite this as f of x is equal to 1/3 the -x plus 2. Or if it doesn't bother you the way it's written, then you can leave it as is. Okay. The negative on the x is negating the x's, which is a reflection about the y-axis. I'm going to go ahead and put negate x's. And then the plus 2 is in the exponent, so being applied to the x's, horizontal shift, left 2. So I'm going to subtract 2 from the x's. There's no stretching or compressing because there's no multiplication, and there's no addition or subtraction outside the exponent, so there's no vertical shifts. Okay. So let's go ahead and transform these with xy tables. My first transformation is to move it left 2. So now my function looks like 1/3 to the x plus 2. To move it to the left 2, I'm going to subtract 2 from the x's of my parent chart. So -2 minus 2 is -4. 0 minus 2 is -2. 2 minus 2 is 0. My y's stay the same. 9, 1, 1/9. Then I reflected about my y-axis, which means that I negate my x's. I have 1/3 to the -x plus 2. I take my x's from the previous table and I negate them, which makes it +4, +2, 0, 9, 1, 1/9. I'm going to go ahead, this is my final xy table. So I'm going to go ahead and plot these points. When x is 4, 1, 2, 3, 4, I'm up at 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. When x is 2, I'm up at 1. And when x is 0, I'm at 1/9. So it looks something like this. And now I just need to decide where my asymptote is. Okay, it was approaching 0 originally in my purple picture, and I moved it to the left. If I move it to the left, it should still be approaching 0. And then I reflected about the y. Notice, if it's approaching 0, if I flip it about the y, it's still going to be approaching 0, just from the opposite direction. So here my asymptote is still at y equals 0. Asymptote at y equals 0. And then I'm just going to find my domain and range based on my blue picture. Domain we know is -infinity to +infinity because it keeps going left and right. My lowest y value is 0, but it's not included, so I use a parenthesis up to my highest y value, which is infinity because it keeps going up. Okay? All right, so on the next page, there's one. It doesn't say practice, but I believe in my heart you can do it. Okay, so I'm going to let y'all do that one, and then number 1 and number 2 that comes after it. So it's 3 for y'all to try. And I will note on this first one, it bothers a lot of people, including myself, when the exponential function isn't written first, or the exponential base. So if it helps you on this first one, you could write this as f of x is equal to -2 raised to the x plus 1 plus 1, if that helps. Okay. I'll give y'all a few minutes to work on these, and then we'll go over them. Okay? Okay, so we're going to go ahead and go over them. The one on the top of the page, I showed you that you could write it as a -2 with an exponent of x plus 1, then plus 1. If you wrote it that way, remember, even though there's a negative in front of it, that represents a reflection. So when you write your parent function, make sure you're only using 2 to the x, not -2 to the x. Okay? Here I picked 4 points. If you only use 3, that's fine. If you use -101, if you use -202, if you use -303, that's fine. You should get the same answer. The other thing to note here is that I scaled my graph a little bit. I went by halves here. If you didn't do that, that's fine. You should get the same general shape. Okay, my blue line here is my original function, which is increasing with an asymptote at 0, and it goes through 0, 1. Excuse me, the transformations are left 1, reflection about the x-axis, and up 1. So when you do that, you should end up with, a decreasing function that is approaching y equals 1 from the negative side. Excuse me. So our domain, again, goes in both directions, left to right, so -infinity to infinity. Our range, we do our lowest y value first. So lowest y value is -infinity up to the highest y value, which in this case is 1, which is where our asymptote is, but we use a parenthesis because we don't include it. Okay. If we look at the next one, number 1, okay, this one should feel a little bit easier if you did the one at the top of the page first. This one only has one transformation, which is to go right 3. And notice on here, I start with my parent function of 2 to the x, and then to go right 3, all I have to do is add 3 to my x's. So I graphed my original here in blue. It's approaching 0. When I move it right 3, it's still approaching 0. So my asymptote is at y equals 0. My domain is going to keep going left and right, so -infinity to infinity. And my range is 0 to infinity because my lowest y value is really, really close to 0 up to positive infinity. When I look at number 2, this is another one you could write with the exponential base first. So if you write f of x is equal to -2 to the negative x and then plus 3, that's fine as well. Okay, whatever helps you. If the 3 doesn't bother you coming first, that's fine. Just make sure you don't use that as your parent function. Okay, 2 is the thing that has the exponent, so 2 is your parent function. So you start out with 2 to the x, make your table, and then you write out all your transformations. So notice I have a negative out of the exponent and I have a negative in the exponent, which means that I have a reflection about both axes, or axes, I guess is how you would say it. So we rotated about the y by negating our x's, and we rotated about the x by negating the y's. Okay. Then we have a plus 3 outside the function, so that moves us up 3. We have 3 transformations. Notice the blue picture is my original with an asymptote at 0. When I reflected about the x and the y and move it up 3, I end up with my black graph here, which notice should be approaching y equals 3 from the negative direction, which gives us a domain of -infinity to infinity and a range of -infinity to 3. Okay. So hopefully we're kind of okay with the process. All the transformation and the tables and all that is the same as when we did this with our regular parent functions. The only thing that's new here is being able to identify the parent function of the exponential, make a table for it, and then knowing where the location of your asymptote is. Okay, so hopefully this part didn't horribly offend anyone. The next piece we're going to go over is solving exponential functions. The way that we solve them is we isolate the exponential base. So meaning whatever it is that has a power, like a to the x equals c, where c is some constant. So we always want to make sure that a to the x or whatever to the x is on one side all by itself. Okay. Then we want to find a common base to rewrite both sides with. So we want to try to write this as something like a to the x equals a to the y. We want to see if we can write both sides with the same base. Because then we have a base exponent property, which basically says that if a to the x equals a to the y, then that implies x equals y. So if I can get some number raised to a base equals the same number raised to another base, then those exponents have to be equal. Okay, so that's where we're headed. An example of that would be something like 2 to the x equals 2 to the 1. That would just mean that x equals 1. So as long as they have these same bases, I can just cancel them basically. Okay, so that's our goal. Isolate the exponential, write them with the same bases, cancel the bases. So let's look at this one. First thing we do is move our constant over so our base is isolated. So I'm going to add 16 to both sides. So I have 4 to the negative x is equal to 16. Now I want to be able to write these with the same base. In this case, we're lucky because notice 16 is the same as 4 squared, right? So I'm just going to replace that 16 with 4 squared. So this means 4 to the negative x is equal to 4 squared. And now that they both are using the base 4, I can reduce those bases away, which means negative x equals 2. And if negative x equals 2, then I can divide by negative 1 on both sides, which means x equals negative 2. Okay, not bad. Isolate the exponential, write them with the same bases, cancel the bases, solve what's left. Let's look at another one. Same thing here. Okay. Any power of 10 will be a 1 with zeros. So if it's like 0.001, 0.01, 1000, okay, those are all powers of 10. And the easiest way to do it is to count the zeros. So notice here I have 1, 2, 3 zeros, which means this is the same as 10 to the third. So I'm just going to rewrite this as 10 to the third, and then it has a negative x exponent is equal to 10 to the x minus 8. Now from our exponential rules in Math 118, remember when you have a power with a base with a power raised to another power, we multiply the powers. So this would give me 10 to the negative 3x equals 10 to the x minus 8. And now they both have a base 10, so we can cancel the bases, which means negative 3x is equal to x minus 8. And then this is something easy to solve. So I just subtract x from both sides. So I have negative 4x is equal to negative 8, and then I divide off the negative 4, which gives me x is equal to 2. Okay. So here my exponentials were already isolated. I had one on each side. So I just had to write them both with a common base, which in this case was 10. And then once I have it written as 10 to some power equals 10 to some power, I can cancel the 10s and solve what's left over. Let's get another one. Oh, excuse me. So now this one has fractions, okay, but we can still do fractions. Fractions can still be raised to powers. So here I have 2/5 to the 2x plus 4 equals 4 over 25. So I want to figure out what these have in connection. Okay, how can I go from 2/5 to 4 over 25? Okay, the way I can do that is I can square it, right? I'm just going to put here 4 over 25 is the same thing as 2/5 squared, right? Because if I square 2, I get 4. If I square 5, I get 25. So I'm just going to replace this 4 over 25 with 2/5 squared. So on the left-hand side, I have 2/5 raised to the 2x plus 4 is equal to 2/5 squared. And then don't forget about the power that's already there. So then this is actually raised to the 11th. Okay? Again, when I have a power raised to another power, I multiply them. So this is 2/5 to the 2x plus 4 is equal to 2/5 raised to the 2 times 11, which would be 22. And now they both have a base of 2/5, so I can drop the base and just set their exponents equal. So 2x plus 4 equals 22. I isolate my variable by subtracting 4, which gives me 2x equals 18, and then I divide off by 2, which tells me that x is equal to 9. Okay. Not too bad, hopefully. Okay. And you can always check these. Once you get your answer, you could plug this back in. I'll show you really quick how to check it. You could plug it back into the original. So you could do 2/5 to the 2 times x, which we got 9 plus 4, equals 4 over 25 to the 11th. Okay. So you could work this out, excuse me, and you could say this is the same as 2/5 raised to the 2 times 9 is 18 plus 4 is 22. And then over here we could still replace this, right? This was 2/5 squared raised to the 11th. So notice we get 2/5 to the 22nd is equal to 2/5 to the 22nd. Or you can actually work it out and see what exactly it equals. But the way to check it is just to plug it back in and make sure you end up with an equal statement or a true statement. Okay. I'm not going to require that you check your answers, but if you like to, that's how. Okay. Let me look at one more, and then I'll have y'all try some. Now this one's a little bit different. On one side we have a fraction, on one side we have a whole number. So we have to figure out how can we write these with the same base. Okay. 4 and 1/4 we have a correlation. Okay, I could write it as 4 to the -1, right? Gives me 1/4. Or I could do 1/4 to the -1 gives me 4, correct? Because I can flip it, right? As long as I use a negative exponent. Or I can think about this as I would like to move this 4 to the top. Okay? If I move that 4 to the top, it becomes 4 to the -1. Okay? Either way you want to do it is fine. So I'm going to move it up, make the 4 to the -1 power. So this gives me 4 to the 3x plus 2 is equal to 4 to the -1. And when I do 4 to the -1 times the 1 that's there, it's just 4 to the -1. So I don't need to write that 1 that was in the numerator anymore. Raised to the -2x. Then again, here on the right-hand side, when you have a number that has a power raised to another power, you multiply those powers. So 4 to the 3x plus 2 is equal to 4 to the 2x. Okay. Now they both have base 4, so we can cancel those, and it leaves me with 3x plus 2 is equal to 2x. I move my 3x to the other side, so all my x's are together. So I get -x equals 2, and then I just divide off the negative, which gives me x is equal to -2. Okay. All right. So on the next page, let me make sure there's more. No. Okay, so on the next page, there's 3 for you to try. I'll give you a few minutes, and then we'll go over them. Okay. All right. So on number 1, first thing I have to do is move my 125, my constant term, to the other side. So I have 5 to the x is equal to 125, and then 125 is the same as 5 cubed. If you're not sure, you know, our lowest base here is 5. So I would just take 5 and do 5 squared, 5 cubed, 5 to the 4th, until I know what power of 5 is the same as 125. Okay, in this case it's to the 3rd. So that means 5 to the x equals 5 to the 3. I can drop the 5's, which means that x equals 3. Okay. On the second one, I'd really like to use 9's. However, 27 is not a power of 9. So I can't use 9 as my common base. I have to use 3. Okay. So 9 is the same as 3 squared, and 27 is the same as 3 cubed. So I just replace that, and then I have to multiply my exponents. So 3 squared raised to the power that was already there, so 2x plus 5. When I distribute those, a big mistake that happens to a lot of people is they forget to distribute it to both. So make sure you do 2 times 2x, which gives you the 4x, 2 times -5, which gives you the -10. Same thing on the right-hand side. When I distribute the 3, 3 times x is 3x, 3 times -2 gives me the -6. Then they both have base 3, so I can cancel those and solve for x. So we should get x equals 4 when you isolate. Okay. And look at the last one. Here I have a base of 7, and I have a base of 1 over 49. So again, remember 49 is the same as 7 squared, right? But here, the squared is in the bottom. So what I have right now is 1 over 49 is the same as 1 over 7 squared. but I need it on the top because I need these bases to be the same. So to move 7 squared up, it becomes 7 to the negative 2. Okay. So I have 7 to the whatever was on that side equals 7 to the negative 2. My 7's are the same, so I can drop them, and I'm left with x squared plus 3x equals negative 2. Now in this case, I have an x squared. So you have to use the quadratic formula or factoring to solve. So I move my 2 to the other side. Here I can do sum product because I need a sum of 3 and a product of 2, which is 2 and 1. And since my leading coefficient is a 1, these are my factors. This factors into x plus 2 times x plus 1, which when I solve each of these will give me negative 2 and negative 1. Okay. So that is the end of E4.1. So you should now be able to complete the E4.1 worksheet, which you need to make sure you scan and email to me or fax in. And you have a regular E4.1 My Math Lab assignment. Okay. If you have any questions, let me know.